Hello, this is Brian Washburn, and today I'd like to give an introduction to the Fourier Series. We're going to be using the Fourier Series in this class when we talk about periodic driving functions. But it's also important to recognize that Fourier Series is really important in many areas of science and mathematics. So let me kind of introduce. So what I have is I'm going to have some function that repeats. So it's a periodic function. F of t is a periodic function. And we can always define a periodic function in such a way that f of t evaluated at t plus some period tau gives me the same function. So that means the function repeats. Okay. So here I give an example. So this could be continuous, completely continuous function. It could be a stepwise continuous function. So here what I have is I have basically this function here. It has a width delta t and it's equal to some value f naught, and it's going to be on from over a time delta t, but then zero and then it repeats with a period tau. Okay, so that's my function. What's a Fourier series? The Fourier series is a expansion of this function in terms of sines and cosines. So I can write an approximate form of the function in such a way f of t is approximated by an infinite sum of sines and cosines, where I have a sub n cosine. So a sub n's are the coefficients for the cosine terms, b sub n's are the coefficients for the sine terms. Okay, and then I just sum over all that. Now notice in the argument I have n. N is an index from 0 to 1 to 2 to 3, such and such. And then omega, what is omega? Omega is 2 pi divided by the period of the function. Okay. And by the way, there's a special term. Really what I should do is I write this as 1 and then add a naught. And there's a constant term, okay, which is the a0 term. The constant term is just going to be equal. So how do I get the terms a sub n's and b n's? I have to do integration. And so the a sub 0 term is a special term. It's basically the area under the function over one period. So I go from negative tau over 2 to tau over 2. That's over one period. Okay. And I divide by tau. So I take this integral. So this is the area under the function divided by the period of the function. That gives me the a sub 0 term. There's no b sub 0 term, but there are a sub n terms and b sub n's. So in order to get these coefficients, I have to do these integrals. Okay, so that's not too bad, and it's fairly straightforward. So what I want to do is show you an example. But before I do that example, I want to talk about these integrations that make life easy, since these are periodic functions. So first of all, I like to talk about even and odd functions. Hopefully you've seen this in your calculus class. Say I have a function f of t, okay, and then what I do is I take in the argument I say minus f of t. I get the same function again, f of t. That's called an even function. Okay, a good example of an even function might be t squared, because if I put in t equals 2, I get 4. If I put t equals minus 2, I get, sorry about that, I get 4 again. Okay, so a function like this, writing it down, y of, sorry about that. So if I write down here, say, f of t is equal to some function f naught t squared, that's an even function, because f of minus 2 is equal to f of 2. Okay. An odd function, what I do is if I take f of a minus argument, I get minus the function again. A good example of an odd function might be f of t is equal to f naught times t. Okay, that's an odd function. T is an odd function. Okay, and if you sketch both of these, so what that's an odd function. So what am I really interested in? I'm interested in integrations over equal bounds for even and odd function. If I have an odd function integrate over one period or equal bounds about 0, I get 0. Okay, and back to our example, you may say, well, you can see that happening. Let me do this. So in talking about even odd functions, what I did was I drew. First of all, I'll take a look at this odd function. This is f of t equals t. Notice that what I have is it's negative on the left-hand side, right on the right hand side. So what I want to do is I want to look at the area under the curve over some equal bounds. So from t to t, or t over 2 or t over 2, it doesn't matter. Some equal bounds about 0. If you notice that this guy has, well, here I have a negative area and here I have a positive area, but the areas are equal to each other. And so what I expect to see is that that's going to give me 0. So that goes back to, again, this relationship that I have here, saying that, well, if I take an odd function and integrate over equal bounds about 0, I'm going to get 0, and that's because the areas cancel. Now, if I have an even function, going back to my even function here, x of t, okay, so here x of t squared, or f of t equals t squared. Notice that here it's symmetric about the y-axis here, and so the area I'm going to get under here is the same area I have under here. Well, it's just a figure. But then what I can say is, well, let's not even integrate from minus t to t. Let's just integrate from 0 to t and call the area 2 times the actual value. Okay, and that's what I get here. So that's going to be very useful for calculating these integrals, because we're always going to be integrating over a period. Okay. Now let's talk a little bit about more over a cycle or period. So in my definition of a sub n's, I go from minus t over 2 to t over 2, tau over 2 to tau over 2, where tau is the period. I don't have to do that. All I have to do is, when I do my integral, I have just to do my integration over one cycle or one period. So I could instead integrate from 0 to tau. Doesn't matter. I'll get the same answer. Okay. But why would you want to do that? Well, it just depends on the functionality of the thing you're integrating. Maybe these bounds might be easier. Maybe these bounds may be easier. So just keep that in mind when we actually do actual problems. Okay. So let's quickly look at an example of a Fourier series. So what I have here is I have a positive square function. It goes up to a value f naught, has a width delta tau, and has a period tau. And notice, I can't write a nice mathematical form except for saying that, well, f of t is equal to f naught over this range here and 0 everywhere else. Okay. Now, in order to express this as a Fourier series, I need to find the a sub n's and the b sub n's. Now, the a sub n's, the b sub n's are going to be equal to 0. Okay. And you may say, well, why is that? Well, the reason why is, remember, going back to my definition, of my Fourier series, a sub n's, these are the coefficients for the symmetric part. Remember, cosine is a symmetric function. Okay. So a sub n's are the coefficients for the cosine. B sub n is a asymmetric function, or odd function, and B sub n's are the coefficients for that. In fact, if you want to get really mathematical, cosine and sine they form a linear basis. Okay, that's something you may learn in a linear algebra class. But first of all, they're orthonormal, meaning that if I integrate cosine t times sine t, they equal 0. If I integrate cosine squared over a period, I'm going to get 1. So they form an orthonormal basis set. Okay, I don't want to get into that right now, but that means that's what allows me to write a function. So that function might have symmetries. Well, it might be odd or even, it might not be either. But in order to express that function, I have to express it as a sum of odd and even functions. Okay, so that's why I have this. So if the function is completely symmetric, which it is, this guy's symmetric about that axis, I expect all the bn's equal to 0. Now you can do the integral. Go ahead, do it. You're going to get 0 if you do it. Okay. Likewise, if I have an odd function, or if this f of t looks odd, then I'll expect all the a sub n's to be 0 and the b sub n's not to be 0. Okay. So let's go back. So what I'm going to do is I'm going to calculate the Fourier series of this guy here. I expect all the b sub n's to be 0 because this is a symmetric function. Okay. About the y-axis here. And so I have to do this integral. Now what integral I'm going to do? I'm going to do the integral 2 divided by tau over 1 period f of t. Now I'm going to break up that, and again I'm going to go from minus tau over 2 to tau over 2. Okay. Now if I go from minus tau over 2 to this point here, it's 0. Okay. So I can say that part's the integral 0. The only part that's going to contribute to the actual integral is going from minus delta tau over 2 to delta of tau over 2. So this part is non-zero, Everything else is 0. So I can ignore that term. And now I have to do the integral of cosine of minus delta tau over 2 to delta over 2. So I'm just finding this area under here. Remember, my bounds of integration from here to here, I have 0, non-zero, and then 0 to there. However, cosine is a even function. And so to calculate the area from here to here, I can just say it's 2 times this area there. And that's what I do. Now I do is instead of going from minus delta tau over 2 to delta tau over 2, I go from 0 to delta tau over 2 and times 2 of all that. So that's an integral even I can handle. That's cosine. And so then what I'm going to get is, well, it resulted integral is 1 over n omega sine. Okay. If I take the derivative of this, I get the argument of this. Then what I do is I express omega in terms of 2 pi divided by tau. That puts tau in the numerator and the tau's go away. Now, you should always, that's actually a good rule of thumb. In the a sub n's, the tau's in the coefficients should all go away. Okay. And the other thing you notice that you have an n in the denominator here. So remember, n equals 1, 2, 3, 4, 5. And so all your a sub n's, as you go to higher values then, they should go off as, they should get smaller with n. Sometimes it's as 1 over n or 1 over n squared, depending on the function. But they should all get smaller. Okay. Now notice this sine term here. Sine can be positive or negative. Okay. And so what you're going to see when you actually calculate these guys out is some are going to be positive, some are going to be negative. Okay. So that's all the a sub n terms. Now we're almost done. We almost forgot the a naught term. The a naught term is just going to be equal to the area under the curve. Again, when I do my bounds of integration, I only have a non-zero value from, sorry, this should be delta t over 2, delta t over 2, and that's going to give me the area. Oh, what's the width? The width is just going to be delta t, delta t divided by t times f naught. Okay, so that's my Fourier series. Okay. Now, what I'd like to do is look at the Fourier series representation of that square wave as a function of number of terms. Okay. Remember, in real life, we can't have an infinite number of terms. They're going to have so many terms. The more terms, the better. Okay, and Fourier series are very useful for numeric representations of periodic functions. So I have here some Python code, Physics 522 Fourier series, that calculates the Fourier series for that square function that we just did, and n is the number of terms I'm going to add in that series. So let's just look at one. Well, let's look at one term. Let's see what that does for us. Notice that here. Okay, well, let's not worry about that. Notice one term, I just have one sine wave. Okay, well, that makes sense. There's only one sine. That is not a good representation of the function. Now let's just add 10 terms. Okay, so that's 10 sine terms. Okay, if I do that, okay, so what I'm saying is here, this graph here is the representation of my square function. Now notice it doesn't look very square. It's kind of peaky here, goes to 0, kind of peaky here, goes to 0. So at least it has the periodicity of the function, but it doesn't look really square at all, and that's because we just don't have a number of terms. Now this bar graph here, which is going to be really, really important, this is a bar graph of all the a sub terms, excluding the a sub 0 terms. So this is a sub 1, a sub 2, a sub 3, 4, 5, 6, 7, 8, 9. Okay, let's not worry about it. That's what we have going on there. Actually, yeah. So those are the terms. Now remember, in some respects, you can think of the Fourier series as a weighted. All those a sub n's are just numbers, and then it's just a weighted sum of cosines. Okay, in this particular case. Now let's add 50. Let's do 50 terms, and you can see, even with 50 terms. So now what I have here, this is my square. Now you notice it's getting more square. Okay, you see some wiggles here, you see some wiggles here, but it's getting more and more square. And then these are all the Fourier components. Now notice as I add more terms, remember I said that sine function get positive, and positive, negative, positive, negative, positive, negative. Okay. Okay, I'll come back to this graph because it's really important. Let's add 100 terms. And you can see here, it's getting pretty square. It's pretty square. But notice that at the edges, I have a lot of wiggles. Wiggle here, Okay, and let's continue doing that. Okay, you can see it's getting pretty square. However, you notice there's always some problem at the at this discontinuity. Okay, and you see these wiggles there. Okay, let's actually zoom in on the wiggles for this. Okay, so what I did was I just kind of zoomed in. Now, what I did in this function, I created a square wave has a period of 1 second, and the width of this is 1/10 of a second. Okay, now take a look. See here, okay, I have some wiggles here, but notice that at the discontinuities, I have a lot of wiggles. Okay, wiggle, wiggle here, wiggle, wiggle here, same thing here and here. Those wiggles have a name. It's called the Gibbs phenomena. And you may say, well, what's that? I mean, think about it. I'm trying to create a very sharp edge using, which is a discontinuity. Okay, it's a piecewise discontinuity with a continuous series, a sum of continuous functions. So there's always going to be some errors. In order to get rid of those wiggles, I have to add a lot of terms. In fact, there's always going to be wiggles if you add a finite number of terms. So those wiggles are called Gibbs phenomena. It's the reason why is because I'm expressing a piecewise continuous function with a continuous function, or sums of continuous functions. That's a cosine in this particular case. Okay. So now what I want to do is let's go back. I'm going to hide this. And so what I want to do is I want to look at this other bar graph. Okay, so again, what I'm doing here is representing this Fourier series with just 500 terms. Okay, and I got this kind of bar graph here. And let's go back to say 50. And again, what does this bar graph represent? This represents the a sub n's. Okay, and you notice that as you go further out and higher, notice that they get smaller and smaller and smaller, as we expected, because all the a sub n's are directly proportional to n. Okay, but there's still, even for 500 terms, or even, goodness, 5,000 terms. Let's see if that even works. There's still going to be non-zero a sub n terms. This guy's going to crank for a little bit. Okay. It's not going to like my plotting. Okay, that's fine. Okay, so you can see there's just a ton of them. Okay, they go to 0 after long term there. Okay, but even it was that 5,000 a little too extreme. Let's do 500 terms. Okay, so you can see they go 0, but still they're not exactly 0. So I want to talk about that. This is really important. Okay, now how do I think about that? Okay, so what is this bar graph? So in principle, I will have a bar graph for a sub n's and b sub n's. I didn't show the b sub n's because they're 0. So basically, one of the way of thinking about the bar graph is it represents the contribution of this term sine n omega t to the Fourier series. Remember, the Fourier series is the sum of sines or cosines. Okay, well, in our case, this should be cosine, but it represents the contribution. Okay, but really, think about all those terms are sine waves. They all have different frequencies because they're all sine waves. Okay, and so basically, that term, that a sub n or b sub n, represents the contribution of that particular sine wave, and a sine wave is a spectral component. So what I like to think about this graph is this graph really represents the spectral content of a periodic function. Okay, and give you just a stupid example. Say my periodic function was cosine. Okay, what's the Fourier series of cosine? Well, it's just one term, cosine. Okay, so if I were to plot the spectral content of that particular guy, okay, what would it look like? Well, it would look like, okay, it would look like just a bar graph. So say I was doing cosine, so all the, so say my Fourier series is f of t is equal to f naught cosine omega t. Okay, well, all the a sub n is just going to be equal to 1. The b sub n's are all going to be equal to 0. Okay, or 1 times f naught. So then what I'm going to get is I'm going to get a very simple bar graph of just that. Okay, where this is n, and these are all the a sub n's. Okay, that's one spectral component. So if I have a periodic function that needs more spectral components, This graph represents the spectral content of that periodic wave. That's a really important concept, and we're going to come back to it multiple times in this class. Okay, so that's all I want to talk about. Again, just to review, mathematically, you learn that, this is very mathematical, and you've probably seen this before. I can represent a periodic function as sums of sines and cosines by just basically doing these integrals. But really, as physics students, what's really important is understanding what the a sub n's and b sub n's mean. And again, the a sub n's and b sub n's mean they are the spectral content of that time-dependent wave. So this bar graph represents how all those sine waves and cosine waves add up to give me the wave I want. In fact, a better way of representing this is a frequency domain representation of my time-dependent function like that. Okay? We'll talk more about that. We'll see you soon. Bye-bye.